Good morning, everyone, and thank you, Ella, for the introduction. So today I will show you illustration of a methodology to do diffraction imaging in a TI media. We know that diffractions are important because they carry information from a wide range of angles, and it's specifically useful for parameter estimation in anisotropic media. Images created with diffractions alone are also quite useful to supplement the interpretation with conventional seismic image. In this presentation, I will illustrate a methodology based on applying weights to Kirchhoff integral in order to mute strong reflections and do the imaging with just weak diffractions. So these weights applied to Kirchhoff integral are built using this concept of specularity. To understand this specularity, let's assume we have a reflection point and we have corresponding source and receiver slowness vectors for the incident and reflected ray respectively. In an anisotropic media, if we decompose these slowness vectors as the component along the normal and as the component onto the reflector interface, then for a specular reflection, the component on the reflector interface are equal according to Snell's law. And for this given arrangement, if we take the sum of these slowness vectors, the sum will align with the normal for a specular reflection. If it's not a specular event, it's a non-specular event, then this sum will deviate from the normal. And the theta here is the angle of deviation from the normal. So Moser and Howard proposed to measure this deviation of events from the Snell's law as cosine of this angle of deviation, which in terms of slownesses is on the slides. For a specular reflection, this angle of deviation is 0, which means the specularity is 1. For a non-specular reflection, this deviation is non-zero, which means the specularity has value between 0 to 1. Alternatively, we found that the formulation of specularity can also be made in terms of the projections on the reflector interface. But for a specular reflection, the sum of projections is 0 for specular reflection, and to keep this definition also consistent with the previous formulation, we subtracted from 1. So this way, this formulation also gives a specularity value 1 for specular reflection, and for non-specular reflection, the specularity value ranging between 0 and 1. So we see this is a very generalized formulation for describing specularity of an event, and we prove with this explanation that I just gave that it works for arbitrary anisotropy as well as mode convergent, which originally it was proposed just for pure mode reflections in isotropic media, but it turns out it has more insight into these equations. So now that we have specularity defined this way, and reflections having specular value 1 and diffractions having specular values less than 1, we can simply build weights to remove the contribution of reflection during Kirchhoff migration. But it's not that simple, and the reason is the reflection comes from an area defined by a Fresnel zone, depending on the frequency content in the data. So let's say the source and receiver are at 2 km and 3 km respectively horizontal position. Then the Fresnel zone for a reflector located at a depth of 2 km could be somewhere between 2 to 3 km or maybe more. So the contribution of reflection for a source at 2 and receiver at 3 would come from an area. So this is an isotropic example, and for this isotropic example I compute specularity values using the two definitions we just showed. So using these two definitions, we see that the specularity values computed for reflection point at the fixed 2 km depth moving from left to right, we plot these specularity values together. So the solid curve is from the definition 1 and the dashed curve is from definition 2. So we see that the reflection contribution is from somewhere between 2 to 3 km, but it still has specularity values less than 1. So another important thing here to notice is that the rate at which this specularity value are changing is different. Specularity values from definition 1 are changing with a rate slower than the specularity value from definition 2, and I will show you what impact this issue has in building diffraction images. So since we cannot simply remove the events that have specularity value 1, it was suggested by Sturzu et al. From Z-Terra that we build the so-called specularity gathers in order to see the distribution of energy according to specularity values. So if we look at this equation, this is a very well-known Kirchhoff integral without any normalization applied to it. And U is the recorded data and capital T is the travel time from source to receiver through the reflection point. So to build specularity gathers, it was suggested to add this additional term to this Kirchhoff integral. It's essentially sorting the data according to the specularity values as bar computed using either definition 1 or definition 2. So this way, if let's say we are doing 2D migration, for 2D case, the output of this equation Vxs is essentially a cube with the third dimension as the specularity dimension. And if we stack over this specularity dimension, we get our conventional image back. But if we build weights such that they remove the contribution of specular energy, which mainly comes from reflection, then we stack over this specularity gathers, we get our diffraction image essentially. So let me repeat it again. If we apply a weight function such that it removes the energy from specular reflections and then stack over the specularity axis, we get the diffraction image back. To illustrate this methodology, we use this simple ramp model example in which the shallow layer is isotropic and the second layer is VTI, and it has the layer has these corners which are possible diffractors, and our objective is to image these scatterers. We perform the ray-based migration knowing that we using the actual velocity fields that we have and build this conventional image. And then I'm going to show you the specularity gathers at certain locations and how can we interpret that which one is the contribution of reflections and which one is the contribution of diffractions. So at this location represented by this vertical blue line, it passes through only reflection point, no scatterers. So what we should be expecting here is most of the energy, reflection energy that's coming from this point, focused towards higher specular values. And these are the specularity gathers computed using the two definitions. On the left side of the panel, the energy is more focused towards higher specularity value. On the right side of the panel, computed using the definition 2 of specularity, the energy is still focused more or less towards higher specularity value, but it's more spread. And the reason it's more spread because, like I mentioned when I compared specularity values, that one using definition 2, it decreases at a rate higher than the definition 1. And these tails going upwards are the migration artifacts, so they stack out when we sum over the specularity axis. And here's the location of the specularity gathers, and these locations actually have scatterers passing through them, and these are the gathers. Since diffractions are weak as compared to reflections, I clipped the amplitude a little bit to see more clearly what's happening in this gather. So there were scatterers present at depth around 2.5 kilometer and at 3 kilometer, and we see that those scatterers produce non-specular energy, and it's spread across all specular values. And it's a similar case in the gather computed using the definition 2. Now our objective is to remove the energy present at certain cutoff, at above certain cutoff for specularity value, and then stack over these gathers to build a diffraction image. Here's another example of the specularity gathers. It just passes through this line passes through just one scatterer, and here's the gather, and from it's also clipped in amplitude image, and there is also smearing of energy at lower specular value. It's just not as prominent as was in the earlier case. But still, choosing an appropriate weight function to remove the specular energy present at higher values, we can construct diffraction image. And these are the weight functions that I choose for this particular example. And after the application of these weights, we stack over the specularity value and get this image that just contains scatterers. This is the image produced using definition 1. This is the image produced using definition 2. And these two images are comparable. So the two specularity formulations we had, they both work. It's just the choice of weight function that differs and should be made appropriately to make these diffraction images. Now we show the application of this to slightly more complicated model. This is a VTI Marmousi model developed by Tariq Al Khalifa. Originally, this model has only VNMO and eta field, but in order to accurately perform the migration, we scaled the eta field to obtain delta field, and this way we have all VP0, epsilon, and delta field. So there are discontinuities along the reflector caused by the faults, and our objective is to image these discontinuities using this methodology. This is epsilon field, delta field, and this is conventional image produced by Kirchhoff migration. And I show you a specularity gather at this location. And the gather looks like this. So using the definition 1, the gather is on the left panel, and we see that there is a still spreading of energy caused by the scatterers at almost all specular value. The panel on the right, it looks more chaotic, but still we can make a decision about the energy that we want to get rid of in order to just build the image with the diffractions. So after making a suitable choice of scatterers, we create this diffraction image using the definition 1, and this is the diffraction image using the definition 2. Again, these two images are comparable. So this methodology has been applied to variety of complicated model, but for isotropic media by Sturzu et al. From Z-Terra, and they have shown then that this technique has potential to image heterogeneities of the form of in the form of fractures or rough edges around salt bodies, and maybe even quantitative characterization of fractures can be done just from these images, which application has been shown by Al-Dajani. So to conclude this presentation, we show you that the specularity can be formulated in two different ways, and we apply these formulations to build the diffraction image, while emphasizing that the choice of this weighting function is important in order to build the diffraction image. Also, we implement this technique for TI media, and we show the example for Marmousi, VTI Marmousi. And another interesting thing is this methodology has potential to extend for parameter estimation using diffractions, and that's what I'm working on in extending this for anisotropic parameter estimation in image domain. And I would like to thank members of I-Team, A-Team, John Stockwell for giving us special lectures from his book Mathematics of Migration, and Dr. Taiminian Moser, who advocates diffraction use in seismic processing, and I had very interesting discussions with him. And also I would like to thank Diane for feedback on presentation, and that's it. Thank you. And I would be happy to take any questions you may have.